record. Yes. All right. We are talking transformations today, just the intro to it. Now, I know that you have seen transformations before at some level. All teachers teach it slightly differently, and so if you have seen it in a different way and it works for you, use that. What I ultimately care about is that you are ending up with the correct graph when it is all said and done, okay? Today, all we're talking about is parent functions and then shifts, vertical and horizontal shifts. And we will add the rest of our transformations tomorrow, put it all together Thursday, review Friday, quiz Monday. What you'll notice is on that cheat sheet that I gave you, it has a place to draw each of our parent functions. It has a table next to it. We will graph from a table of favorite points, and I call them favorite points, key points, a lot. You don't necessarily have to memorize them. You can rebuild these tables every time because all you're doing is plugging numbers into the function. What I do expect is that you can graph all of these. Our graphing calculators are now done for about the next week and a half. They can take a break, okay? Because we're going to graph these by hand perfectly using dots, starting with our table. Now, what you're going to notice as I build my key points is that there is kind of a minimum amount in there. As long as you know the shape, a couple of them will tell you where to go. Some of you will want to extend your tables a little bit more to give you a little information. Let me give you an example. F of x equals x squared is our first parent function. My minimum points I would put on that would be like -1, 0, and 1. And I would plug those into the equation. -1 squared is 1, 0 squared is 0, 1 squared is 1. As I put those on the graph, they would go here. But if I do not know what shape I am drawing, I might need a little bit more to help me with. So if you don't know the shape of a particular function, because I'm going to show you later one that has these exact same 3 points and is a different shape, okay? I may extend this a little bit, like include like -2 and 2. -2 squared is 4, 2 squared is 4, and it helps me draw in my shape a little bit better here. But for sure, I have to get those 3 ones right there in the middle. This is a nice, smooth curve forming a parabola through those points. While we are doing this, as we are doing transformations, I'm going to have a conversation with my people that have really small handwriting right now. It is an expectation that I can see your dots on there. So make sure that you are drawing dots big enough that I can see. Sometimes we kind of put them there for our own purposes, and then like our line covers them up. Make them obvious, okay? Because I am basically going to make sure that you know where those dots exactly were supposed to be. This is all exact graphing from here on out. Okay, so next one. Again, what points would I bare minimum use to draw an x cubed graph? Again, I would go that -1 to 1. I would only go those bare minimum if I know the shape of the graph. -1 cubed is -1. 0 cubed is 0, 1 cubed is 1, and again, if I put those points out here, now I know the shape of this graph, that's enough for me. However, if that looks like a line to you and you would draw it as a line, you need a few more points. It's not a line. If I put in like -2 and 2, you can see, and this runs off my graph, so it's unfortunately, but -2 goes down to -8. 2 goes up to +8, and you can see that it is not a line, that it is going to increase very quickly. It's going to then squiggle through my origin at those 3 points and then increase very quickly again. So you have to know the correct shape if you're going to use those bare minimum points. Let me know if I click through a page too quickly for you. Next parent function, absolute value. This is the one I was talking about earlier. If we look at the bare minimum points of -1, 0, and 1, you get the exact same things that you got when I had the x squared graph of 1, 0, and 1. Which again, if I put those in my picture, right now based on those 3 dots, I would have to know the shape that's supposed to go in here. And if I don't, I would extend to -2 and 2. The absolute value -2 is 2. Absolute value 2 is 2. And the shape of an absolute value graph is a sharp V, not a smooth curve like a parabola. You have to very clearly draw the difference in those two shapes. Questions? Okay, next parent function is the square root graph. F of x equals the square root of x. Now, this is the first time that we will go away from that negative 1 to 1 favorite points. I am the one building this table, so I would pick these strategically. First of all, I know I cannot square root a negative number, so I would not include a negative number here. I also don't want to have to guess what they are, so I'm only going to pick numbers that I can actually take the square root of, like 0. So I'm going to pick what we would call perfect squares. What's the next perfect square? 1. Square root of 0 is 0, square root of 1 is 1. What's my next perfect square? 4. My next one way runs off the graph, but if you had like a big graph to work with, you could include 9, right? See, I would only pick numbers that I can nicely, I would not put like square root of 2. I don't know what the square root of 2 is, and it would be an approximation anyway. Only pick ones that I can nicely square root. Put those points out there. Know, again, the shape of the graph. 0, 0, 1, 1, 4, 2. Knowing that I start at that 0, 0 dot and do not extend past it to the left. To the right, I'm going to curve through these, and then it will slowly continue to curve and rise as we move to the right. It would not get up to 3 till we got all the way out to 9, right? It's going to slowly increase. Okay. Next one is the cube root graph. This one, again, you will notice this same set of points showed up already, and this is where, again, I have to know the shape of the graph or extend my points in here. I would, again, pick perfect cubes. Now, cubes are a little bit different than square roots. Negative 1 is a perfect cube. The cube root of negative 1 is negative 1. Cube root of 0 is 0. Cube root of 1 is 1. We've already seen these 3 points, so if you don't know the shape of this cube root graph, you might need to extend, because again, it's not a line, and it's not the same shape we saw before. My other perfect cubes, does anyone know what the next perfect cube is after 1? 8 and negative 8. Cube root of negative 8 is negative 2. Cube root of 8 is 2. Again, kind of runs off my graph here, but negative 8, negative 2 would be somewhere about here-ish. 8, 2 would be about here-ish, and you can see that this graph then increases very slowly. It then squiggles through my origin and continues to increase very slowly. If you don't know that shape, you need to extend your table all the way to negative 8 and 8. Questions so far? Okay, we have completed all of the parent functions that we will actively see in this section. We are going to talk about the rest of the parent functions. The first one is the rational function, or fancy word for fraction. Okay, we are going to spend like an entire section, an entire several days / then take a DCA over it, on how to graph a rational function. So yes, it is one of our parent functions, but we're going to look at it later. I will show you what it looks like right now. It has a weird set of favorite points, and that is this. 1/2, 1, and 2 would be the favorite points that I would put in here. If I were to graph that, first of all, I'm going to start with 1. If I plug that into my function, 1 over 1 is 1. 2 is also easy. 1 over 2 is 2. If I plug a half in there, 1 divided by a half is the same thing as 1 times the reciprocal, which is why you see that this answer ends up being 2. 1 divided by a half is 2. Those points look like this. This can never be 0, and I can't plug in 0, right? Because if I had a 0 in the bottom, it would give me an undefined. Hold on just a second. As I plug in bigger and bigger x's, it's going to become a really small fraction, but it'll never be 0. And so what you'll see as I draw my line through these is that it's going to slide close to my y-axis, but never actually get there. It's going to corner through those 3 points, and then it's going to slide close to my x-axis, but never get there. And that's half of your graph. The other half is just repeated on the negative side. And so the same 3 points in the negative side would give me -2, -1, a half. And I get the same corner in quadrant 3, in the negative direction. Again, slides along my axis, corners through those 3 points, slides along my axis. That's about the last time we're going to talk about that function right now. Like I said, we have an entire section dedicated to the rational function and graphing it later on in chapter 2. The other function that we are going to, yes, it is a parent function. We have got 2 more of them that are parent functions, are not the ones that we will talk about during our transformations chapter, is first of all this one, f of x equals x. It is also your linear function. We usually see it as y equals mx plus b, and that's how we would graph it. We would not think through transformations to graph that. We would graph it as y equals mx plus b. It is a parent function, so we will add it to our list of parent functions. This is your most basic linear equation, y equals x, okay? So if I were to do my -1, 0, 1, plug that in, I get -1, 0, 1. This time the line actually is a line of dots here. And that would be your basic y equals mx plus b, or the one that goes through the origin with a slope of up 1 over 1. And our final one, that again, yes, it is a parent function. It is the last time we will talk about it in this section because we just will not apply transformations to move it, is when it says f of x equals c, where c is a constant or a just plain old number. If we remember, we have talked about this, if constant function is going to be a horizontal line, so whatever that number is, it doesn't matter what I plug into my table. When I plug it into that function, I get whatever that constant is. Let's pretend that it's something like 2 would be a horizontal line up at 2. And again, yes, horizontal lines, y equals a constant, are parent functions. It's the last time we have that conversation in this section because we just won't apply transformations to that. It's not a function that we would transform. As we get into this chapter, I will tell you that you are not doing anything with your graphing calculators, that we will do everything by hand. You will utilize your table of points. You will utilize what you know about functions, and I will teach you that. However, to get started, I'm going to look at what it would look like on a calculator. Now, again, knowing that you guys have a little bit of intro to this probably, depending on where you're coming from, before we have seen this. So what I want to show you is I graphed 3 things on my nice graphing calculator that is done in color. And you can see what happened to each of these. I started with the parent function x squared. There it is in blue, centered at the origin. Okay. The next equation I typed in was this x minus 3, which is in red, and it ended up here. And the last one I typed in was x plus 5, and you can see that it is in green, and it ended up here. First of all, from our original parent function, what direction are you seeing my graphs move? Left and right, okay? Now, when I say left and right on a graph, and then I say something like minus or negative, which direction would your head think if I were to say left and right and negative? Left, okay? But did our graph move left when we subtracted? No. So that is the one of the challenges with transformations, is that it turns out when things are inside of our function, they will always behave opposite of what we think that it should. So yes, it says minus 3, but in reality, it moved our graph to the right 3. What you guys are looking at are what I call, it's the transformations left or right. The mathematical word for that is a horizontal transformation or a horizontal shift. How do we get a horizontal shift? We will add or subtract a number on the inside of our function. And we're going to spend some time later talking about the inside of our function and outside of our function. So positive then, or adding, would actually move our graph to the left. and subtracting will actually move our graph to the right. Okay, similarly for this transformation, again, I started with our parent function x squared centered at our origin. Notice the difference. I used the same two things, minus 3 and plus 5, but notice now there's no parentheses up here. The minus 3 would be considered what's outside of our function. Same thing with the plus 5, outside of our function. So which direction are they now moving? Up and down. Now, do they move the way we think they should? Yes. This time the subtraction moves down, which is the way we would normally associate that with a graph, right? Negative moving down, positive moving up. These are what are called vertical transformations or vertical shifts. Up and down, okay? Again, adding and subtracting. The only transformations we are looking at today are with addition and subtraction. The difference is that addition or subtraction happening inside or outside of our function. And if it is outside of our function, we know that that will move it up and down the way we think it should. Positive moving us up, negative moving us down. Okay, so we've referred to the inside and outside of a function, and what's important is that we understand where those things are located. Now, a lot of times I think it can be kind of obvious, especially if we're talking something like an absolute value or square root function. But with things like exponential functions, it's not always as obvious what is inside or what is outside of your function. So I just want to take a second and address what would be examples of inside and outside. Notice I have grouped some of them together. Your exponential, both x squared and x cubed, your inside and outside look the same. It doesn't matter if your exponent is a 2 or a 3, okay? Same thing for your radical, cube root, square root. It doesn't matter which type of root you're taking. Your inside and outside will look the same. So let's go ahead and talk about this first type, exponents, when we've got exponents. Inside requires you to have parentheses. If it is not physically inside of parentheses, it is not considered inside of your x squared or x cubed function. Now, with pluses and minuses, I think that's decently obvious where we had like the x plus 1, plus 1 squared compared to over here where we would not have it inside the parentheses, x squared plus 1. It's really the multiplication that always catches people on this. Whether it's multiplication of a number or with a negative, again, the parentheses is a must for it to be considered inside. So let me show you side by side here. It'd be the difference of something like negative 4x cubed. That negative and the 4 would both be considered inside because of the parentheses, compared to negative 4x cubed, that is now considered outside of the function. And it is that particular one right there that is typically where people have the issues with inside versus outside of the function. I will show you the rest. A lot of the rest of them are pretty intuitive. When we get to things like an absolute value, it's literally, is it inside the bars or outside the bars? Okay. So an example of something inside of our function would be like the absolute value of x plus 5, where both are grouped inside of your absolute value bars, compared to absolute value of x and the absolute value bar plus 5. That would be now considered outside of your function. Same thing with your radicals. Inside versus outside is it underneath the radical bar? Okay, whether it's in a square root or a cube root. So again, the difference between an inside and an outside would be something like the cube root of x minus 7, where the minus 7 again happens underneath the bar, compared to like the square root of x minus 7. Notice I ended the radical bar, and that minus 7 would now be considered outside the function. Again, I will talk about this, but it's not really the focus of our section right here as far as inside and outside. This one can also be a little bit complex as far as figuring out inside versus outside. This would look like something like inside has to be inside the denominator. So like x plus 2 would be considered inside that function. If it's separate from the fraction, it would be considered outside the function, like 1 over x plus 2 would be what outside of that function would look like. And again, if I were to give you any advice, it's to make sure that you understand this concept. It's really the multiplication and the exponential ones that are where people have the inside versus outside confusion. Okay, anyone still need this page? Today, we are just focusing on the transformation that is vertical and horizontal shifts. This is a mnemonic device that you will see located on the back of your note sheet at the very bottom. Now, it is not a typo that it's at the very bottom, even though it's the first one we're talking about. Eventually this week, we will have all of these boxes filled in, because these are all of the different types of transformations that can happen. When we have multiple transformations, you actually have to attack them in the order that they are on this paper. We are learning this bottom one first, but it's actually the last thing that you would address with your graph if you had more than one thing going on here. So let's start at that bottom box where it says shifts. These are both vertical and horizontal. This is a mnemonic device. ILROUD is how I refer to it. If you don't know how to spell it, it won't help you. Normally I don't care about spelling, but mnemonic devices, it's kind of like the key thing to those. Anyway, it stands for this, inside. Moves us left, positive. Negative moves us right. O stands for outside. Positive moves us up. Negative moves us down. Now let's talk about how I would actually graph this when I get to graphing this. I would start with my table of favorite points at the very top. I would apply all of the transformations to my table as I'm working my way down this table, or down this page. But once I get to the bottom, I would take my table of points, whatever it looks like at that point, and I would dot out the table of points. Okay, so when I get to this very last box, to apply these transformations, I would start by just putting dots in the picture where my table is currently. From there, I would count left or right, I would count up or down to get to my final graph. So I'm just telling you right now, I do not adjust my table of points when I get to this point. I would dot them out wherever they are. I would count in my picture and put my dot in its final place. Because this is the last transformation you apply anyway, you would not have to move them from there after all, so that you don't need a table at that point. And I really find it easiest to not have to figure out, am I adding to the X or the Y column, blah, blah, blah. Just count in your picture. Okay, are we ready to try one? Okay, please understand how we attack transformations. People get like ahead of themselves. Let's look at the question. We only have 2 of these today, by the way, for your notes-taking purposes, this and one other variety. It says, use the graph of, and it gives you the parent function. That's what they are going to identify in the directions here. Use the graph of the parent function to graph the following. So you ignore the following for a second, and you just create your table from your parent function. I am not going to address the whole transformation thing right now. We just go find that f of x equals x cubed table. Now, if I go find that, it was -2, -1, 0, 1, and 2. Cubing each of those, -8, -1, 0, 1, and 8. Then I start applying transformations. Okay, I will always, this table 100% always just comes from whatever we just wrote on our cheat sheet. Okay, people are like, well, what about the -4? Now I address that. So now I go to what I'm supposed to be doing, and I do that to this graph. Well, there's only one transformation. It is a plus or minus, which means it has moved us down to this last box. In that last box, it said dot out our table and count that in the picture. Okay, so if I dot out my table, I have these points, -2, -8, -1, -1, 0, 0, 1, 1, 2, 8. And now I go to my transformations. Inside or outside? Outside. Outside moves us which direction? Down. So I'm going to move us down 4. That would be the description of what I'm doing. Now I'm going to go do it in my picture. I'm going to take each of these points individually. I have 5 points in that picture. I go to each of those 5 points and count down 4. 1, 2, 3, which is off my picture. That's okay. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And those green dots then would be that transformed graph. Questions? Okay. That is how we attack it if they are trying to go from a parent function. Okay, so one of those ones that's on our cheat sheet, we go get the table of points. Sometimes they will do just some random weird looking function. Okay, now progressing to like tomorrow and Thursday, yeah, that is not a parent function. So I don't have a table, but could I create a table from those points? Absolutely. I could come off to the side here and say, I just list all the points I see in the picture. -2, 0, 0, 3, 2, 0, 4, -3, 6, 0. I just listed those little 5 points that are highlighted in the picture, and I now have a table to work with. We don't really need that today because we're just doing the shifts at the bottom. So actually what I needed is where those graphed. Well, they already took care of that for me. So then we go to the transformations. Notice the difference in the notation. This is not a parent function, so they have to use what's called generic function notation. Just using our function notation, they're saying the graph we're going to graph is this original one. Now, can you tell me the difference between these two being inside versus outside? Is it decently obvious? Okay, perfect. So inside would move us which direction? Right? Opposite of what we think, right? Right 2. So all I have to do is come over here and count each of those dots to the right 2, and we're done. To the right 2. Actually, I'm going to use something other. That's blue. Right 2. Right 2. Right 2. Right 2. Right 2. And that first one would have ended up here. Okay. Versus this one, which again, hopefully from your function notation, you can tell if that is inside or outside, and that is outside. We are moving which direction? Down. So we're going to move down 3. So I take each of those 5 points from the original. I move them 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3, 1, 2, 3, and that's where that one would have ended up. Questions? Okay, so I don't have, that's not a parent function. I don't have a table of points. I could create it from the picture if I wanted to. Tomorrow we're going to want to. But that's all I have to do. Go move the dots that they give me. Okay? We're going to do just this one for our check for understanding. So if you have your dry erase marker handy, please grab that. While you are getting that ready, I just want to show you, it says, begin by graphing the square root function f of x equals the square root of x. They're basically saying go find your parent function, right? Use the transformation to graph this one. So you're going to then have a picture of h of x on your table. Okay? See how you would attack this one. If you are not sure where to start, please call me over. You got it. You may. Ooh, check again. Use this one. Which direction are you going right now? Yes. Yep. Do them together, so like a combo. It looks like you did one separately and one separately. It's actually the combo of those two together. While I'm kind of coming around checking how we're doing here, I do have your test graded. They are in Power School. I've got several people that are still have not taken yet. So I am going to wait another day or two to like show you the answers and hand them back and go over questions. But you can see your scores right now. And they will come soon. All right, so what's the +2 on the inside? Where's that going to move us? Okay, so we're going to take that dot and go, I think you went right. Does that make sense? Okay. Okay. Yeah. Start with your x squared. You're going to want this table of points right here. So that's your basis. And then you're going to count from there. The +2 and the -2, which the direction they move us. Yes, do that last. All right, guys, the +2 in this one is the one that's going to throw people off because it goes against what we would do intuitively, right? When we are thinking on a graph, my parent function, which would just be f of x equals the square root of x. So we go to get that table of points, which was 0, 1, 4. So the dots 0, 0, 1, 1, and then 1, 2, 3, 4, 2. Our transformations that are happening, and again, this is a combination here. I do both of these. +2 on the inside is the one that's going to catch us. Slow down. Inside, we have to think opposite. We should have moved left 2. This one right here is outside my function. That one moves the way I think it should, down 2. So now to every point, I apply both of those things together. I would take this point, I will move left 2, down 2, that's where my final point will be. Left 2, down 2, that's where my final point will go. Left 2, down 2, that's where my final point will go. Starts at now at that -2, hits my x-axis, not where I drew it, at 2, 0, and continues to rise slowly to the right. Questions? All right, your assignment is number 13 on My Math Lab.